This presentation is about an augmented reality framework for collaborative service robots, and it's a tool to help improve human-robot interaction. Here are some key terms that are central to the project. The first one is human-robot interaction, which is a field dedicated to understanding, designing, and evaluating robotic systems for use by or with humans. The second is augmented reality, which is a technology that creates a composite view of the real world and artificial elements. The future is not just robots. The future is human and robot collaboration. Think of R2-D2 and Luke from the movie Star Wars. In the real world, robots are no longer working in isolation. They're delivering boxes and products to humans, traversing the aftermaths of natural disasters and sending information back to humans, and they are taking humans on informational tours throughout museums. So safety and understanding between humans and robots is more important than ever. Here is a quick project overview. Robots are central to this project. So in our lab, we use TurtleBots, which are 3-foot robots with a Roomba base. The robots have 3D laser scan, camera, and motion sensors. While the robot is traversing through a hallway full of students or an office with chairs and desks, it collects information using its sensors so it can avoid obstacles and reach its destination. To operate the TurtleBot, we use a platform called ROS, which stands for Robot Operating System. In our project, we send real-time information the robot is collecting through its sensors to a platform called Unity, which is a game development tool we use to create a functional app. Unity allows us to create and project images in augmented reality corresponding to robotic sensor data. We are able to build our Hypercube app for iOS and Android devices, as well as Microsoft's HoloLens. Here's a small clip of the robot showing its laser scan through augmented reality on an iPad. The cube on top of the robot is used for tracking its position. Our app essentially acts as a translation device. It takes in robotic language, which is thousands of numbers, and then it translates it to a human-readable form, which is meaningful symbols, colors, and animations. Now we will delve a little deeper into how this app was actually created. First, we have network communication. In order to transfer data, we needed to construct a communication pathway from the robot to the app. The robot is controlled by ROS, which again stands for Robot Operating System, and the app was built using Unity. To allow these two modules to exchange streams of data, a WebSocket connection, which is a protocol for allowing communication over a single TCP connection, was required. This was implemented using ROS's ROS Bridge package, which provides a WebSocket connection and allows communication between browsers in the form of JSON. The next step was data filtration. Using ROS, the TurtleBot is able to convey information by publishing real-time data under a certain topic name. Each topic is packaged in a different way. For instance, the pose point topic indicates the current location of the robot in its map, and it is in the form of floating point coordinates x, y, and z. There are many topics, so to control which topics we want to listen to on the app side, we wrote various scripts in Unity that subscribe to specific ROS topics. These scripts also allowed us to filter, reduce, and control the rate at which information was being sent, which helped reduce bandwidth and latency issues. As a result, the app has a smooth and visually appealing transition during each update cycle. Third is data transformation. The topics published by the robot are sometimes in different frames of references. For instance, the robot's path is in the frame of reference of odometry, but we needed it to be in the frame of reference of baselink, which is the robot's base position. To fix this problem, we used open-source ROS packages and mathematical algorithms to transform the required data to be in the baselink frame of reference. The next step was visuals. After the proper data was coming in, I wrote scripts in Unity that worked with particle systems. Particle systems are essentially an array of objects that you can set positions, colors, and sizes for. When creating visuals, it was important to keep in mind colors, animations, and symbols that would most effectively communicate the meaning of the information to the user. For example, we used a grid of color-coded circles for the cost map, where red circles represent where the robot can't go, and green circles represent where it's safe for the robot to go. This video shows the turtlebot trying to travel to its goal point but then getting stuck along the way. The green circles show the turtlebot's intended path. Towards the end of the video, you can see the turtlebot getting stuck near the wall. Usually, to understand why this failure happened, you'd have to look through ROS topics or parse through code. But with our app, it's clear that the robot is malfunctioning because its intended path is actually going through the wall. So this tells us that the robot's map is off or that its localization in its map is incorrect. The next step was building the Unity program so that it could be deployed as an iOS app. This was one of the most difficult aspects of the project for me because I was using a tool I was unfamiliar with to debug a process that I was also unfamiliar with. It took me a bit over a week to become comfortable enough with Xcode to debug properly, and it took days of research to tackle the errors that prevented the app from building. Creating a user-friendly interface was another important part of this project. It required developing code to connect the user's input in toggles and input fields to other scripts in the app that controlled what information was being displayed. Currently, our Hypercube app is being used in a human-robot navigation research study. The research study will examine how augmented reality affects a human and robot crossing paths in a tight hallway. We believe blinkers, similar to those of cars, will allow the human to know where the robot is planning to go, allowing him or her to avoid that path. To make this research study possible, some additions were made to the app. For instance, I'm working on creating a custom blinker message in Topic in ROS, which allows Unity to know if the robot is planning to go left or right. The Hypercube app has various applications in the real world. For instance, in education, it allows young students to interact with robots without having to parse through thousands of lines of code. In search and rescue missions, we see our app allowing rescuers to deploy robots to search tight or dangerous spaces without endangering themselves. In manufacturing, our app would have the potential to lower the expertise barrier of employees who are allowed to work with robots, as well as reduce casualties. This concludes my presentation. Thank you so much for taking the time to listen.